In the previous video, we looked at a horizontal spring mass oscillator. We're now going to jump straight into the slightly more difficult case of a vertical spring mass oscillator. And this is slightly more difficult because you've also got the weight of the mass to contend with. Just like in the horizontal case, we will be treating the spring as light, so we don't have to worry about the mass of the spring. And it's going to be vertical at all times. Okay, you're not going to be bouncing around with a motion that's like this. That's too complicated for this course. So what happens is you've got this mass hanging from a spring, and if you pull it down vertically below to where it is, then what's going to happen is the spring is going to pull it back up, and then it's going to push it back down, and it's going to oscillate vertically under SHM. So let's have a look at the setup. First of all, without the mass on it, what we're going to find is the spring is going to have some kind of natural length where it doesn't have a mass on the end, which I'm going to call L0. So it's just the natural length of the spring. It's just the length of the spring. There's no forces acting on it. But for this to be an equilibrium, the spring needs to be longer than L0. So that's not the case with the horizontal spring mass oscillator because there wasn't the weight it had to balance with. But here we've got the weight to balance with. So if this is the equilibrium position, that is, if we left it there, it wouldn't move, then the spring is not at its natural length. So what I'm going to do is I'm going to say that the displacement x is up here. Okay, so the natural length of the spring, L0, goes from there to there. That's a fixed number. And for the equilibrium position, we have to extend the spring by some amount so that the weight balances the tension in the spring. Okay, so the forces up equals the forces down. That would be the equilibrium position. And ultimately, when we are undergoing the simple harmonic motion of the system, then the equilibrium position is the center of the oscillation, not the natural length. So it's going to bob up and down about this equilibrium point. Okay. So really what we want to do is we want to not have the extension of the spring as our variable x. We're going to want really the displacement from this equilibrium position, because that is the center of the oscillations. So first of all, let's have a look at the equilibrium position. So at equilibrium, we want the tension in the spring, which we're using Hooke's law again. So we're going to say that is equal to Kx. Okay, where is the extension? So Kx. That's the force up. We want that to equal the force down, which is mg. So at the equilibrium position, x is actually equal to mg on k. Okay, so there are three main factors now which affect where the equilibrium position is. M, so the bigger the mass, the more the spring needs to extend to get to equilibrium. G, which is obviously a constant on Earth, but it does mean that if you're on a different planet, then that would change the equilibrium position relative to the natural length. And also K, but it's dividing by K. So the stronger the spring is, the less distance it needs to go, which again makes sense. It's essentially the stiffness of the spring, isn't it? So if the spring is stiffer, then it can exert more of a force earlier on to get that equilibrium. So that will shrink the equilibrium distance. Okay, so this distance here, therefore, again, it's a fixed distance because all of these are constants, m, g, and k. Okay. So really what we want is we want to define a new variable, which I'm going to call y, which is another displacement variable, but it's defined from the center of oscillations. Okay, so let's first of all form a differential equation in y. So at any given time t, we have got the weight downwards, mg. We have got the force upwards, which is kx. And then the displacement is y. So if I apply F equals ma to the situation, Down is positive, okay, because my displacement vector is defined downwards. So I'm going to get mg, subtract kx, and that's going to equal times m times the velocity. Now the velocity in this case is y double dot, which actually would be the same as x double dot, as you'll see shortly. So this isn't quite SHM, because I've got this constant kicking around, and I've also got a y and an x. But even if that was x double dot, it still wouldn't quite be SHM because I've got this this constant. So what I'm going to do is I'm going to translate this whole system so that y is my variable. In other words, I'm going to redefine x in terms of y, and then put that in here, and then what should happen is the constants will cancel. So what I've done to get from x to y is I've moved it in the x direction by y. Therefore, by translation theory and kind of regular maths, I'm actually subtracting the distance between those. So mg over k. Okay, so y equals mg minus x minus mg over k. Okay, and that translates this kind of coordinate vector down in the positive x direction by mg on k. Okay. So if I use this substitution in here, that should get rid of my constants, because the mass will oscillate about that point. That is the centre of oscillation. So that's why this transformation will make this an SHM equation. Okay, so if I actually do that, I'm going to get mg minus kx, but x is y plus mg on k, and that's going to equal mass times acceleration, which is y double dot. We can see then we're going to get mg minus k times mg on k, so the k's cancel, and then mg minus mg is 0. So that's going to give me my differential equation, y double dot plus, it's going to be ky is equal to 0, which is now my equation for SHM, so that is SHM. Oh, divided by n, sorry. I forgot to divide by n. So that is my equation for SHM, which is exactly the same equation as the horizontal case, except it's not the extension now that is my variable. It's the displacement from the centre of oscillation. So if the spring is, if the question is going to be asking about the extension of the spring at any given time, you need to then kind of translate the solution here back into x, because x is the extension of the spring, not y. Okay, so just be careful, and that's what makes these questions a little bit more difficult, because the centre of oscillation, the equilibrium position, is different to the extension point, the natural length of the spring. Okay. Example 1. Okay, so let's see this in action. So we've got a spring of natural length 2 meters. It's got one end attached to the ceiling and one end attached to a particle which has a mass of 2 kilograms. And this is vertically below A. And any questions like this, you'll always be in that vertical plane. Given that T, the tension in the spring, is 28x newtons, so again we can see Hooke's law coming into play. The tension is proportional to the extension, where x is the extension of the spring. Show that this is true. Okay, so we're going to show that that differential equation is true. Just notice that this is x, where x is the extension. We're told in the question x is the extension of the spring. Okay, so if I say that I'm up here for my extension, that then defines x. And when I define something like that as an axis variable, I mean that x is 0 here and then increases going downwards. So that's essentially what that means. So if you're up here, then x is negative. Okay, so by Hooke's law, the force acting upwards is the tension force, which we're told is 28x newtons. And then we've also got the weight of our object, which, because it has a mass of 2, then its weight is going to be 19.6, or 2g, if you like. Okay. In fact, because there's g in the question, I'm actually going to write that as 2g. Okay. And now it's going to apply F equals ma to this setup. So F equals ma. the overall force is going to be 2g minus 28x is equal to the mass times the acceleration. Mass is 2. And then if I take that equation and divide it by 2, then that'll give me the solution that I want. So I get x double dot is going to be equal to g minus 14x. And that's just me taking that equation and dividing it by 2. Okay. All right, so that's the governing equation of my setup. Okay, part B. State the value of the spring extension when the particle is in equilibrium. Okay, so for equilibrium, that means the resultant force, F, is going to be 0. That's something you just need to know from kind of your A-level mechanics. So that is knowledge that this exam can pull upon. That means then that the acceleration is 0, because F equals ma. And if the acceleration is 0, then that means then that g minus 14x is 0. So if g minus 14x equals 0, then I'll get a value for x. So if g minus 14x is 0, then x is going to be g, which is 9.8 divided by 14, which is 0.7. So when x is 0.7, then the mass, the particle, sorry, is in equilibrium. Okay. Right, to part C. Stating numbers for A and B. Use the relationship y equals ax plus b to transform star into this form. So we can see this is now in standard SHM equation form. And star is actually this, this equation here. So we're going to transform this into this, and we're going to use that theory that I talked about earlier. So if I need to translate this by 0.7, okay, that's the value of x until we get to our equilibrium position, and that means that this variable, which I'm going to call y, must be equal to x minus 0.7, okay, because I've translated it by 0.7 in the x direction. If I want to make this translation, then I can see that A must be 1 and B must be minus 0.7, okay, because that's the translation I need to use. Okay. So if I let A equal 1 and B equal minus 0.7, then this transformation will transform my answer from A into the answer that it wants. All right, so just to recall my answer from A, that was x double dot is equal to g minus 14x. Now, if I let y equal x minus 0.7, then that'll get rid of the g essentially. Also, we'll notice here that y equals x minus 0.7, because it's just a translation. Then if I double differentiate this, I'll end up with y double dot is equal to x double dot, as promised. I did say that earlier. Okay, so if I run that through, then the x double dot here is just going to become the y double dot, and the x here is going to become the y plus 0.7. So that's going to equal g minus 14x, but I'm going to write x as y plus 0.7. And what we'll find is the 14 times 0.7 is g, which will cancel with the g. So I'll end up with y double dot is equal to minus 14y. And that tells me that y double dot plus 14y equals 0, which is exactly the form it wants. And we can see that omega in this case would be root 14. All right, and finally, for example number 1. The particle is held at rest with AB 3 meters. The particle is given an initial velocity of 1 meter per second upwards. Find the extension of the spring in terms of t for the subsequent motion. Okay, so now that we know that this is the governing equation, then I can solve this differential equation, and I'll end up with a solution, and you can just state the solution from the given equation. I have to run through the auxiliary equation, etc. I'm going to get that y is some constant times the cosine of root 14t plus some other constant times the sine of root 14t. And then if I differentiate that, I'm going to get y dot is equal to minus a root 14 times the sine of root 14t. I'm going to get plus b times root 14 times the cosine of root 14t. Okay. Now I can use my initial conditions. So the particle is held at rest with AB 3 meters. Now I need to find the value of y when AB is 3 meters. So let's just go back to the question. I already know that its natural length is 2 meters because that was in the question. It's also 0.7 meters below that because I need to get to the equilibrium position, and then I can start defining y. So if my whole distance AB is 3 meters, then y is the difference between that and this point. So therefore y is 0.3 meters, because then 2 plus 0.7 plus the 0.3 would give you the 3 meters that AB is. Okay, so just be careful with that. So the particle's held at rest with AB 3 meters, so that means that when t equals 0, y equals 0.3 and y dot equals 1 meter per second upwards, so negative 1, because in all of my workings downwards has been positive, but it's been launched upwards, so therefore it's in the negative direction. Okay, so if I plug these conditions into here, I will get then that A is going to be 0.3, because when t is 0 that will disappear, and that'll be the number 1. And b root 14 is negative 1, so therefore b must be negative root 14 on 14. Okay. And now that I've got that, I can state y, which is going to be 0.3 times the cosine of root 14t minus root 14 on 14 times the sine of root 14t. That is the solution. Okay, find the extension of the spring in terms of t and the subsequent motion. So that's the solution to this differential equation at the top of the screen here. However, it's actually asked for the extension of the spring, which is not what y is. Y is the displacement below the equilibrium position. If I want to get the displacement of the spring, I need x equals, which is the definition of my displacement, which is going to be y, so same function above, but then I need to add that 0.7 back on again, times the sine of root 14t plus 0.7. And that is because, if I go back to the top of this page, I'm using, where did I put it? Oh yeah, I put A is 1 and B is minus 0.7. So I'm using the relationship y equals x minus 0.7, so therefore x equals y plus 0.7. So if I wanted to get x, then I have to take y and then add 0.7 to it to get back to x. Okay, so that's that question. And then very quickly I want to talk about example 2, which I'm just going to talk about it, I'm not going to write anything. So example 2 is a similar setup, but it's attached by an extensible string. So we've got particle P is attached by a light extensible string to the ceiling. This is a string, not a spring. The natural length of the string is 0.8, and the equilibrium length of the string for mass m at the end of the string is 1 meter. Okay. Okay. So, part A, describe the subsequent motion of the particle if the string is extended to 1.1 meters and the particle is released from rest. So essentially what we've got here is we've got a situation where we've got the mass down here, we've got the equilibrium, we've got the extension up here, and then we've got the equilibrium here, and the difference between those two is 0.2, because the natural length is 0.8, and when it's in equilibrium, then the string is 1, so therefore that distance there is 0.2. Now for part A, what we're looking at is a situation where it's extended to 1.1, so the mass is pulled down to here, which is 0.3 from the natural length. Okay, so it's 1.1. So if it's pulled down to here and then let go, then what's going to happen is you're going to get some kind of sinusoidal motion because it's going to undergo SHM. That's all fine, all very well and good. That'd be exactly the same motion if it was a spring as well. And the reason for that is because if that distance there is 0.1, then that distance there is also going to be 0.1, which means that the extension of my spring never goes negative. Okay, it's always going to be between, x is always going to be between 0.1 and 0.3, which is great because that means the string is always in tension, which means it's always going to have that, that tension present. But for part B, we've got a slightly different situation. We're going to repeat the same situation, but this time the string is extended to an initial length of 1.3 meters. So again, let's just draw my little diagram out. We've got y here from the center of oscillation. We've got x up here. That's still 0.2. That was fixed from the question. But this time it's pulled down to 1.3, which means extension is 0.5. So that means it's going to be 0.3 below here. So it's going to be pulled down to kind of this length. Which means if it's going to undergo SHM, then x needs to be negative because we're 0.3 below, which means we need to be 0.3 above. The problem is that the string can't push back on the mass if x is negative. So what we actually get is we get this part of the motion, which is kind of the first part of SHM. Let's do a solid line. That distance is 0.3. That distance is 0.2. That's when x is 0. That's all very well and good, but for SHM to occur properly, the string needs to push back down on the mass now, which it can't do. So we don't actually have perfect SHM anymore. We actually have a little parabolic cap on the top where it's free falling. It's essentially a projectile for that period of time because the only force acting on my mass is its weight. There's no tension force because the string in that moment is slack. So we've got some kind of projectile coming up because it's got some kind of initial velocity. It's free falling under gravity, so it's a parabolic cap on top of my trig function there. It's going to have the same gradient, so it kind of blends quite nicely. And then when it gets back down to here again, the string is then going to get taut again. And then by symmetry, that's the same velocity as this. So therefore, we are then going to end up with a situation which does that. And that distance there is 0.1. Now, on the surface of it, it does look like SHM. But what you'll actually find is that if you model this as a spring and you model this as a string, then as time goes on, these two solutions will deviate significantly until you wouldn't have thought they had the same starting conditions. And occasionally they'll come back into sync again, and then they'll come back out of sync again. But it's not quite a perfect sinusoidal wave because you've got this cosine wave which goes up to here, and then you've just got a parabola. And then you've got the cosine wave again, and then you've got a parabola. And the parabola is here rather than the cosine wave because there's no tension in the string at that point, and it can't give a negative tension. It can't give a thrust force. It doesn't push back when it's slack, as a spring would. So I think that's probably above the scope of this course, but I think it's quite an interesting case, which is why I wanted to mention it in this video. Yeah, that's just modelling difference between spring and a string. Yeah, as I said, no difference here because the string would always be taut, because x is always between 0.1 and 0.3, whereas here, if you wanted SHM, x would have to be between minus 0.1 and 0.5, which the string can't do the negative x values. Okay, cool. Right, thanks very much for watching. I'm going to stop there. If you've got any questions, then just drop them in the comments below, and I'll get back to you.